I'm Laura Cosgrove. I'm a senior data scientist on the Microsoft Experimentation platform team. I've been on the team for 2 years, and I'm really excited to speak with you today. I'm an individual contributor, so I'm just hoping to share basically from the ground what it's like to be a methodologist on an experimentation platform team. So who is Microsoft EXP? We operate the A/B testing platform for Microsoft, and we serve many teams across Microsoft of all varying sizes. We were founded in 2006, but we certainly haven't been working with all of the Microsoft teams since 2006, so we really span the full life cycle. And our mission is to empower product teams to innovate and make data-driven decisions through trustworthy experimentation at scale. If you're newer to online A/B testing, I think this is a very technical conference, so maybe not, but the key point is that experimentation means that we can causally attribute outcomes like metrics to the changes we make to a platform through random assignment and quantifiable uncertainty or variance. The role of a methodologist on an experimentation platform team, I'm going to touch on a little bit today as I go through my case studies. What our work aims to do is to identify opportunities to improve trustworthy decision-making and update our methodology in response to new scenarios, develop methodology-informed user experiences, how are users consuming the insights that from an experiment on our platform in a trustworthy way. What we don't aim to do, which is a trade-off of being on a platform team, is we don't aim to optimize the analysis for one or a few experiments, and we don't aim to own policies or decisions for our partner teams. So the value that I hope to provide is how do we take a problem and understand whether it's worth generalizing across the platform, and if so, work with engineering to embed it into our analysis process. A little bit about the platform. So we're supporting multiple compute backends, Spark, our SQL language called Cosmos, along with the experiment needs of like many organizations, as I discussed earlier. And scale-wise, we're at over 100,000 experiments a year. And I put this diagram up here because I want to describe how the process starts with raw data, logs, sometimes a very good data store, sometimes extremely raw, like event streams. That's partner owned. And in purple is what our platform runs for every analysis. So we have a standardized code generation and compute based on some inputs that the partner teams gives us through metrics and an analysis request. And then in yellow is what we have like easy access to, our summarized data, our meta-analysis of experiments. We call them scorecards. What this means for a methodologist, and what I'll talk to you today, is that the test code generation of the analysis methodology and simulation is really essential to characterize that platform performance, what was in that purple box. Where it starts is that as a data scientist, I generate test data with some known properties. And write test code that works on that test data to get this summarized data and also performance statistics about our proposed methodology because we own and understand this test data properties. And optionally, for certain questions, we might need to pull sample raw data from our partners to really ground our methodology improvements in realistic performance characteristics. This comes in our production platform through our integration testing framework. I won't talk too much about this today, but a lot of people on my team do really cool stuff around how we test our platform end to end to make sure that our methodology has known statistical properties and that we're making the right trustworthy decisions. But really, this is a talk about like this investigation, validation, feedback loop. The translation work from a partner comes to us with this problem or we notice this weird phenomenon in our data, and we want to understand, like, is there a methodology improvement to be made here? And the tools that I'm going to use today in this talk is simulation studies to characterize the methods and estimators we're proposing. I also want to mention our goal is to reduce this funnel. Our goal is not to create every ticket that someone makes on our platform and put it into a platform feature. We want to understand whether through investigation validation, whether it's worth it to invest further. All right, so that's my little introduction. We're going to talk about grounding our investigation with simulated data. And we have 2 case studies that really uses that tool. I'll talk about sizing our impact with that summarized data, that yellow box from our platform. And that's comes up in the second case study. And then the final case study is using some sample raw data to simulate a realistic performance of a candidate method, which is machine learning assisted VR. Okay, so let's get into the case studies. Variance reduction with heterogeneity. First, I want to give a quick background of variance reduction. I like this analogy from a blog post here. Imagine every time we calculate a metric, like a mean and a value in a treatment, a mean value in control, a delta between treatment and control. It's like shooting an arrow at this bullseye. And for evaluations, we have candidate estimators, which is a few different ways of estimating the same thing. Each of these candidate estimators can be in some of these buckets. Either it's high bias and low variance, high variance, low bias. We want to be able to put our estimators in this bucket. The key idea behind variance reduction is that we want to build a better estimator by knowing that a user's past behavior is a predictor of their future behavior. So heavy users are heavy users, light users are light users, or at least there's a relationship between their previous activity in a previous week and an activity in the experiment period. How can we leverage that information? We adjust with our variance reduced estimator. We use QPED at Microsoft. We adjust for the explained variance in the post-experiment period and reduce the sample standard deviation while keeping the metric an unbiased estimator. And this is more about communication. How do we communicate how well we did? If we're just producing this variance reduced estimate, how do we say that there was any value taken? So this is a UX decision. We created this concept called an effective traffic multiplier, which is, the insight is that for a given test, the ratio of unadjusted estimated variance, so the normal like t-test estimated variance, to the raw variance estimates the amount of traffic that would need to be added to our t-test estimator to provide the same level of variance reduction as VR. So it's like you're multiplying your traffic by using this estimator. For free, you get to a situation where you are moving an estimator from a high variance estimator to a lower variance estimator with the use of a user's past data. So that's just a quick intro to VR. There's a blog post if you guys are interested about further insights here, but I'm going to get into a stress test for VR. This problem came up in our platform where when we launched this feature in our UX to communicate the value of variance reduction, this effective traffic multiplier, we got a few odd screenshots sent our way. We told users that they needed more traffic using the VR estimator, not less. And where did we find this was happening in general when we investigated? Usually in segments of an analysis. So where this pointed us, we looked at the literature a little bit, was to the area of heterogeneous treatment effects. And this is actually a known weak point of VR, these types of VR estimators. And the logic goes like this. In a good situation for VR, where treatment is not modifying this relationship between the AA value and the AB value, residuals are small in treatment, small in control, and if you average it together when you're estimating delta, you get a nice variance-reduced estimate. However, in this heterogeneous scenario where treatment is modifying the relationship between the pre-experiment value and the post-experiment value, you can actually get variance inflation. This is a really weak point in VR. It's kind of a known limitation when we looked into it. So the question is, can we identify good candidate estimators to smooth over this weak point of VR? So because the goal is to ground theoretical performance, I benchmark with fully simulated data, and it's the stress test scenario where I'm simulating high heterogeneity and low sample size. So these are our fighters: current CUPID, which Microsoft implements for variance reduction, and a couple of other estimators from literature. And the key hypothesis is that one of these estimators is going to be a little better in this scenario, ANCOVA2, and some details in the linked papers because of that. But what did we find? We found that the true efficiency gain and average bias for all of these estimators were like nominally different from one another. Average bias centered around 0, which is great. True efficiency gain, effectively 0. When we looked at this effective traffic multiplier performance estimate that we're reporting, we saw that for a few of the estimators, like the one we had today, we're kind of reporting this like scary effective traffic multiplier quite a lot of the time. My idea for a better CUPID, one that aligns a little bit more with ANCOVA2, which should be better under this scenario, never reported this effective traffic multiplier less than 1. And for a second, I was like, oh, this is great. Maybe I should go ahead and suggest this as a methodology improvement. Savvy listeners might expect that because we're reporting this performance effective traffic multiplier less than 1 none of the time for this better CUPID estimator, it's actually indicating that our variance estimate for that estimator is incorrect. So since all of the estimators have identical simulation-based variance, this is closest to what we should report. And this is something where what we found as a UX pain point really does reflect true performance of the estimator. And there was no easy place to turn to say, hey, this is a no-brainer. Let's implement this alternate methodology. Okay. So overall, what we learned from this quick case study is that an effective traffic multiplier in an individual study is just an estimate of the variance reduction of the estimator. And it's more likely that it's less than 1 when there's truly no gain from regression-adjusted estimators, which applies in these situations that you might encounter in an experimentation platform. And if we are thinking about making methodology improvements to CUPID to align a little bit better with this estimator from literature that we know does slightly better in this scenario, we'll need to do additional work to improve the variance estimate. Ultimately, we knew that it would not resolve this scary effective traffic multiplier estimate that motivated this work. Estimators are very close. We kicked this case study out of the funnel. Okay, that's a teaser. My second case study is about safe deployment. This question came in. As a feature owner, I'm following safe deployment practices when A/B testing. And what that means is that I start my new test feature with the rollout steps from 10 to 30 to 50%, kind of slowly exposing my population. There's consistent treatment assignment between steps. And when ramping up, I monitor my metrics in my analysis, and I want to monitor greater than or equal to 7-day metrics before shipping to 100%. We want to have that policy for our decisions. For EXP, or for users using EXP, the default is step level analysis. So step is that 10, 30, 50 step. So for this feature owner, the minimum date to get 7-day insights is day 12. A stage level analysis, which stage is just the name for this traffic where all else is the same except for the ramp up. This might give us a 7-day insight at day 7. Can we deliver that to get 7-day insights faster? So to answer this question, we have to think about what true scenarios could be underlying this, the outcomes of interest for this feature owner. So just thinking about a 7-day analysis, it might detect a constant treatment effect with more power versus a 1-day analysis. Or it might detect a time-dependent treatment effect, such as like a treatment effect that increases with exposure length. Or it might detect a heterogeneous effect, which could be any shape that is reliant on a pre-experiment covariate, such as a light or heavy user. Quickly, I wanted to level set with related work. What kinds of metrics or outcomes are we measuring in an experimentation platform? Overall, we tend to measure open-ended metrics on our platform. So users endogenously appear in the experiment according to their usage pattern. They're assigned on the fly, and we greedily take all available data when we build a metric for our analysis. So if it's average minutes played, you treat the user with a partial day session, the same as a user who appeared every day. Cohort-based metrics are a little bit different. They condition on time since exposure. And what that means is that open-ended metrics have a moving target dependent on time. So like looking at the equation on the side here, the first delta at day 1 is the difference in observed outcome between user 1 and user 2. And moving to delta at day 2, that second row, we have the difference in observed outcomes again from days 1 and days 2. We accrue new information from the new users, but we have dependence from the old users in the analysis. And this time dependence of what we're trying to estimate, the estimate, interferes with, one, for Spotify, there's assumptions behind sequential analysis, which is why they invested in figuring this out. And mechanically, that means they move to a longitudinal modeling approach. And the key point that they needed to do is to estimate the correlation between estimates at day 1 versus estimates at day 3. A couple of references there, like really great work by Spotify. So when I was thinking about the implications of this work for my question, how do we get to crossed-up analysis? I knew that I had to anchor on what I'm trying to estimate and be really careful about that question. We want to ground how well we're delivering a value for the user that corresponds to a true treatment effect that they're trying to answer. So what I did, I benchmarked with fully simulated data, but I mimicked this realistic rollout and analysis policy. In this counterfactual world, the outcomes I'm simulating for users, they can come in endogenously. They're randomly assigned to one of these buckets that may or may not get a treatment, and they have these 1, 3, and 7-day versions of their metric, which could be dependent on exposure length if I'm simulating time dependence. So just lesson learned from when I did this, it's really important to set up an estimate that makes sense. I took a few winding paths. I kind of first thought about conditioning on a user that appeared eligible for treatment, but the appropriate targets take into account these true potential outcomes based on the whole experiment period, as well as the exposure length, to try to avoid conditioning on the endogenous effect of a user's likelihood of appearing in the analysis period. So here's the estimates. Here's what we're trying to estimate, what happened. Depending on the time dependence of the treatment effect, you can see that, so this x-axis here, I realize in this room it's a little small, but we have our stage scoped scorecards here and our step scope scorecards here. If you have no time dependence in your treatment effect, it's absolutely fine to stage scope an analysis to report a 7-day effect at 7 days. You're not gonna, even if you have day effects, trend and metric values over days, historical usage affecting metrics, you're not going to go wrong. But if you have time-dependent treatment effects, depending on exposure length, you poorly estimate these conditional treatment effects based on 1, 3, and 7 days, and you poorly estimate it even worse for when you're diluting existing users with new users. So the implications, we want to turn to cohort-based metrics for this scenario and for sequential testing. our platform as we look to the future for getting user-based metrics and sequential testing. And we want to take a lesson that user-based sequential testing needs to model the time structure. We also learned that cross-step analysis is valid without time-dependent effects. Can we estimate this potential application with real aggregated data, the summarized data from our platform? So that's another problem. How do we estimate if we're in a world of average treatment effects? What we can do is test the difference in Kates equals 0. The point estimate is the Kate at day 7 minus the Kate at day 1. You kind of ignore the assumed positive correlation between these two summary statistics, and we get to a sort of swag estimator of the time dependence of treatment effects. Yeah. Sorry, just a rough estimator. We're not perfect, but we're kind of roughly approximating with summarized data. That makes sense. Oh yeah, also please ask questions. I didn't say that at the beginning. So just grounding this on the partner application, what we found is basically 18% of rollouts with the data that was available could be recommended cross-step analysis. This could save about 7 days for our partners in 18% of rollouts. And bringing it back to our implications, we decided that this naive approach of cross-step analysis is not sufficient for the majority of future rollouts, and we're going to invest deeper into improving time to decision with our sequential testing implementation. So that's the conclusion of this case study here. This last case study is about ML-assisted multivariate variance reduction. What is the expected gain from extending VR implementation to a multivariate option? So today we have this algorithm called CUPID, which relies on a specific metric value. It's just a univariate regression of the pre-experiment period on the post-experiment period. We also offer metrics that don't have variance reduction enabled, which is the vast majority of metrics. And we got this question from our partners: what is the opportunity for using machine learning to assist variance reduction and make it a more optimal metric where we're detecting more changes at the same sample size? Our choices for multivariate VR, I'm going from the lower cost to the higher cost. You can think of cost as just cost of implementation, cost of maintenance. We could do multilinear regression with a fixed list of covariates. We could do sort of multilinear regression with all covariates available. We could do a machine learning assisted method where we transform the list of available covariates in a linear fashion to predict the outcome, or we could use some nonlinear methods to predict the outcome. And there's some details why that cost is ordered. We also have like pretty strong priors, like that higher efficacy of the or we'll get the best variance reduction efficacy if we go with the most complex approach that we tested. Because we want to simulate realistic performance with our partners, we're using real sample A versus A tests from a few partners. And when I talk about the list of covariates, it's the list of metrics that they're registering with us in our platform that we can then materialize for them in views for the pre-experiment period, and choose for each metric we're going to regress against all these other metrics or a transformed version like in these options. Our model evaluation was a little bit interesting. Because we're trying to use sample raw data and predict at the same time, we needed to avoid the estimation bias, which is induced by regularization and overfitting from the machine learning estimators. This is an idea from double machine learning strategies where you're both estimating estimating the machine learning estimator and also the delta or the metric value at the same time. In our situation, we just use the training folds for creating our predictive covariate that we would use to reduce the variance of our estimator and evaluate the t-test, the metric value on the test folds. We average this. Subsampling, we would average this across all the iterations. We did the same thing for the non-machine learning models, keep it comparable. What we found, it didn't really shock us that much, but a couple of interesting things that happened. So this is a couple partners we tested this on. Orange is what we have today. The baseline, of course, no variance reduction, so that's all normalized to that. We found that just including a per day segment in the metric value that we're regressing by got us pretty far to improving variance reduction. And we did observe that this nonlinear method of variance reduction did perform best. But overall, a lot of the gain came from just this pretty simple strategy to add a date-segmented covariate. So that's sort of the platform decision we made. This is the winner. And this is what we're integrating into our product. This is a little bit of a technical lesson, my last little nugget. But something I learned from using this case study data to characterize an estimator is that subsampling, I described, you're pulling this raw data, we're kind of subsampling to get this estimator performance, can be a little bit misleading. We knew that it was important to assess value for confidence around this variance reduction decision to understand if what we were measuring, the difference in variance reduction was just noise, or is this expected to reoccur in this population of data. We simulated the variance reduction, the confidence intervals around that, and then also the bias and the average bias interval. We first tried just subsampling the data. We didn't perturb the variant assignment columns at all. And we found a significant bias away from zero. We got a little worried, oh, is our theory wrong? And then we kind of thought about it a little bit more and we realized we're missing a level of variation more here. And what you need to do if you're working with raw data and you're trying to characterize this estimator is you need to bootstrap, resample, or shuffle your assignment column in order to get a sort of performance estimate of your estimator that makes some theoretical sense. Just a little lesson. So overall, this is the end of my talk. I went through some questions, implications, lessons. We talked about VR performance with heterogeneous treatment effects, insights, getting 7-day insights faster in a rollout scenario, and the expected gain from extending VR implementation to a multivariate option. I want to acknowledge Ada Wang, who helped a lot with the last case study, doing that study with me. Jen Townsend, my manager, and the whole Microsoft EXP team. And here's some slide references for my references. Thank you.